let us see some preparations and the properties of this carboxylic acids. Carboxylic acids will contain two functional groups. One is carbonyl group plus the other one is hydroxy group. This is the carbonyl group. This is hydroxy group. In fact, these compounds have two functional groups. C double bond O, that is carbonyl group. Actually, all the properties of that carbonyl group already studied. But what happened here, a carboxylic group means the carbonyl group is attached to the lone pair of the OH, which shows a resonance. Therefore, this C double bond O, which is actually supposed to show the properties of nucleophilic addition reactions. This should undergo nucleophilic addition reactions. These properties almost it is vanished, you do not find at all, because of the resonance stability or the delocalization of double bond. When this happens to be shows this resonance, the structure will have a single bond between the C and the oxygen, but whereas this oxygen will become out of the two lone pairs, one is given. So, the plus charge will come, this will become. So, specifically this carbonyl group many times will exist as a single bond. So, therefore, the point of that addition reaction will not arise. So, because of that delocalization of the double bond, the nucleophilic addition reactions, which is a characteristic reaction of carbonyl group, is totally disappeared, almost 90%, more than 90%, you do not find at all. But the OH group, oftenly that is hydroxy group, which was there in the alcohols or phenols, will show such properties, reaction with sodium or some acidic property, or the replacement of the OH with a so called PCl5, such reagents, the halogenation takes place. Such reactions you find in the carbox. That is, some of the properties of OH are retained, but the most of the properties of carbonyl properties you do not find at all. Because of the two groups attached, it has a resonance stability after donation of the proton. So, let us say this group gives away the proton. What comes is a RCOO minus. This is called carboxylate anion. Now, this has a beautiful resonance. The O minus will come and this will go, and you will get another resonance structure in which O minus will become this side double bond O. So, the carboxylate anion has a very good resonance. Therefore, the donation of the proton will become easy. This property is known as the acidic property. So, the addition reactions totally disappeared, but the hydroxy properties, some of the properties of OH are retained. In addition to this, a new property, because of the resonance stability of the carboxylate anion, it ready to lose the proton, the consequent the anion formed has a resonance stability. Therefore, the carboxylic acids are very much known for the proton donating. In fact, their name also we have given a carboxylic acid, carbonyl plus hydroxy, carboxy plus acid, because it is giving the proton readily. So, we named this compound also as a carboxylic acid. So, these compounds are well known from the long time, and we have acetic acid commonly used, one of the member, that is called vinegar, a CH3COOH, which is commonly as a 5% solution used as a vinegar in the cooking dishes and all that, preserving the chilies and all that. We know very much the vinegar under the name vinegar. The other acids, even the butyric acid, other acids also, the acids with hydroxy groups like tartaric acid, citric acid, malic acid, these are also well known compounds. Hydroxy acids, carbonyl group containing acids, pyruvic acid, all these acids are prominent members in the biological, the cycles and all that. So, the carboxylic acids preparations and the properties, let us see. So, let us go for some of the preparation methods of of these some carboxylic acids. One such method is a oxidation method. Oxidation of 1 degree alcohols as well as aldehydes, because 1 degree alcohols in fact first gives aldehydes only. So, let us have one common representation RCH2OH, and mild oxidizing reagents, they are converted into the C double bond O, the H aldehydes are formed. This is 1 degree alcohol this is. So, OH attached carbon has one alkyl, therefore, it is called 1 degree alcohol. This for this conversion you can use a common reagent like copper at 300 degrees centigrade. Copper at 300 degrees centigrade, this reaction takes place. It is a removal of HH, 2 hydrogens comes out as a hydrogen gas. So, the copper is only a catalyzing metal here, 2 hydrogens removal is minus of H2, you can call it as a dehydrogenation, but the compound is oxidized. So, the reaction is oxidation and it is a mild oxidation. And the next step, if a reagent like a tolerance reagent, very mild, again mild oxidizing reagents like ammonical silver nitrate, Fehling's reagent, or any mild oxidizing like dilute permanganate or dichromate can oxidize to give the next step carboxylic acid. So, in this oxidation the number of carbons we are not neither increasing or decreasing, same number of carbons are present in the alcohol, comes to the aldehyde, comes to the acid. So, if 3 carbon alcohol is taken, corresponding 3 carbon propanaldehyde is formed and then gives propanoic acid. Both the steps are very convenient and mild reactions. However, you can do this reaction with a dilute sulfuric acid in combination with any oxidizing agent like permanganate or dichromate. When you add, the alcohols gives aldehydes and consequently immediately oxidize to acids. You can say direct method, but obviously it passes through the aldehydes. But if you use copper, the reaction comes at aldehyde and stops there. You have to do second oxidation like ammonical silver nitrate or any mild oxidizing agent which will convert into the acid. So, this is a 2-step reaction, but this is a 1-step reaction, right. Similarly, you can go for the hydrolysis steps. Hydrolysis of alkyl cyanides RCN, or you can take it as a RCONH2, this is called amide. Either cyanides or amides on hydrolysis will give the acids. The cyanide will contain a triple bond. Selectively you can hydrolyze to give the amide using the alkaline, that is sodium hydrogen peroxide in presence of the basic medium, that is NaOH. A unique reagent, it is alkaline hydrogen peroxide. Hydrolysis or partial hydrolysis takes place. You will get a OH will be getting like this. Actually, a sort of hydration is taking place on the CN bond. This tautomerizes, in fact, immediately tautomerizes to give the amide formation. The amides undergo further hydrolysis with the aqueous NaOH if you take and hydrolyze it or boil for some time. The ammonia undergoes hydrolysis, HOH if you add the H which NH2 ammonia gas will come, this becomes into the acid. But the point you can remember that whenever you use the basic medium, the acid cannot be the final answer. So, you get in the form of the sodium salt. Sodium salt of carboxylic acid will come, because it is basic medium, the ammonia released will be rejected out, it comes out as a ammonia gas. So, the nitrogen part comes as ammonia gas and the RCO part will become into the acid. So, if you take the propane nitrile or ethyl cyanide, propane nitrile will give corresponding propane amide and then gives the propanoic acid. So, within directly also you can propose here also with taking the aqueous NaOH and boil for some time. So, it will become the amide and then undergoes hydrolysis to give the acid. So, in this the amide is happens to be one of the acid derivative. So, therefore, you too can have another method. It is not the only amide, all other acid derivatives also on hydrolysis will give the carboxylic acid. That can be taken as a third preparation method. So, let us go for the third method, that is hydrolysis of all acid derivatives that is a carboxylic acid can have a acid halides like acid chloride, you can have a acid anhydride, you can also take a ester, you can also take RCO NH2 amide. Just now we have taken the amides hydrolysis. All these are all actually prepared from the acids only. Therefore, generally from this getting back acid is not commercially that useful, except in the two cases. One is an ester, that is naturally we are having a glycerides, that is triglycerides, esters of the glycerol in the nature as a oils and fats we have. So, the source of that esters, if you hydrolyze, you will get glycerol out and the other side you will get the carboxylic acid. Or natural amides are there, they are proteins and all that, they also on hydrolysis you will get the. So, for these two cases natural sources are there. Anhydrides and acid halides are very reactive, they do not be available in the nature. So, therefore, commercially these are prepared from the carboxylic acid, therefore, there is no point in preparing acid from these two derivatives, these are highly reactive. But as a matter of fact, you can show the reaction that any one of these compound, if you just add water, first to actually with water anything is required, just add water and nothing is required, just you will get the carboxylic acid as a one of the derivative, the other side this corresponding answer. But in the later two you need water and some catalyst like either acidic medium or basic medium. As I said, the acid is the one, so therefore, better take the base. So, both esters and amides in alkaline medium readily undergoes hydrolysis to give the acids. So, in the first case you will get the another byproduct alcohol, in the last one case you will get the carboxylic acid plus ammonia as a one of the byproduct. So, all compounds undergo hydrolysis, but as I said the first two are highly reactive, just you add water you get the products plus heat is liberated. So, the first two reactions are exothermic reactions, but the last two reactions are if you boil then only you will get the reaction, that means they are endothermic reaction, they are stable. So, therefore, unless you boil and then you will not get the carboxylic acid. But as a matter of fact, theoretically all the four can be converted into their corresponding acids by a simple hydrolysis technique. The stability order also, the acid chlorides are more reactive towards hydrolysis than anhydrides, then esters and then amides. So, amides are more stable, therefore, the conversion will be slightly difficult. So, question may be asked, which of the following immediately turns into the acid, or which of the following difficult to convert into acid, or hydrolysis is difficult, slow hydrolysis, fast hydrolysis. Okay. More the reactive, faster will be the formation. More the stable the compound, less reaction or hydrolysis will be slow. So, this is all the hydrolysis of the carboxylic acids. Let us go for the another method, that is adding the RMGX to the carboxylic acid using a RMGX, which is a well known reagent known as Grignard's reagent, and carbon dioxide. RMGX is a very versatile reagent which can be added to several compounds like carbonyl compounds and so on. But on the carbon dioxide also you can add RMGX RMGX undergoes a nucleophilic addition, R adds on the carbon, magnesium plus adds on the O. So, you will get corresponding salt formation RCOO minus MgX plus. So, this undergoes hydrolysis with the water or acidified water, then you get the corresponding acid, a carboxylic acid is formed. So, the CO2 which you have taken will be the last COO group is from the carbon dioxide, the R comes as a RCOH. Let us say for example, a 6 carbon oic acid if you want, you take carbon dioxide plus 5 carbon containing RMGX, this 5 plus 1 will become into 6 carbon. So, last COOH is actually generated from the carbon dioxide. Carbon dioxide is a quite a stable compound, generally will not include or involve in the reactions. The credit goes to the RMGX because highly reactive compound which will add on the gaseous very stable compound. The reaction definitely requires a high pressure and temperature. Then the salt formed on hydrolysis will give the acid formation. There is one more method we have. Let us see one more method, that is the fifth method for the preparation of carboxylic acid. This is ozonolysis. Ozonolysis of alkenes and alkynes, both ene and ine functional groups can be ozonized. Like for example, if it is disubstituted alkene, both the sides 1,1 alkyl group containing alkene can be conveniently first treated with ozone gas, that is called addition of ozone will give the ozonide formation. Then do hydrolysis with water. If you add zinc, then what happens? Zinc takes away the oxygen, both the side you will get aldehydes. So, therefore, nothing should be taken, just water only. This is called oxidative the ozonolysis. If you add zinc or any reducing agent like nascent hydrogen or dimethyl sulfur, such reagents if you add, one of the O out of O3 will be taken by this reagent, this side that side 1,1O, both will become aldehydes. So, this is called oxidative ozonolysis, oxidative or special ozonolysis it is called. If you use a zinc or such reagents, that is called reductive ozonolysis. So, oxidative ozonolysis of disubstituted alkenes will cut into two pieces. This side one acid, the other side one more acid, two pieces of acids will come, and depending upon the R1 and R2, what are the R's you have taken, corresponding R's will be coming. You too can have an alkynes containing this type, same reaction will give to, that is first do the, this should be separate, do not mix water and ozone together. First add ozone, treat it with enough time, ozone is added and undergoes a rearrangement, the mol ozonide will become into ozonide. That ozonide treat it with only water, no reducing agent mixed again. So, this is called again oxidative ozonolysis. Will cut this compound into two pieces, you will get the carboxylic acid and carboxylic acid. No loss, no gain basis, two carboxylic acids will be formed. So, both are very good methods for the converting the alkenes and alkynes. If in the alkynes there is no chance of having the two R's this side that side, that only one R will be there. Here we have a chance dialkyl. If dialkyl is taken, you are going to get a ketone. So, that is why selectively only 1,2 dialkyl type of the alkenes only you have to take. 1,1 type of dialkyl if you take, one side ketone will come, the other side one carbon will become acid, that is not useful. So, therefore, take the two R's on each side 1,1, so that both the sides you will get the carboxylic acid. On this beautiful, the only the on the preparation also there is one good problem is there, I will give that problem. Once in a IIT examination there was one problem like this. The data given is like this, actually a flow sheet type of the representation I made. Compound A with the molecular formula C8H10 treated with ozone followed by hydrolysis with water, that is, this is ordinary hydrolysis, that is oxidative ozonolysis it is. So, that gave the B, compound B. Compound B must be a carboxylic acid maybe, because on oxidative ozonolysis generally answers will be the acids. We can guess that may be an acid. The data as such it is not given, but we can guess one point B may be a carboxylic acid. And another data is given, there is a compound C with the formula C3H5Cl. This is the molecular formula he suggested already. Treating with magnesium in dry ether, C converts into D. So, if this is a Rx, then with magnesium what comes is RMGX. As I said in the last but one method, in the fourth method, the RMGX on reaction with CO2 by hydrolysis you will get the RCOOH. So, that is this carbon is induced into the compound, the B will become a RCOOH. So, the R which we have taken here has become into the RMGX, that is Greganode reagent, which is treated with the consequently with the CO2 followed by hydrolysis gave a carboxylic acid. So, what is this the Rx means? We know C3H5Cl. If it is really propyl chloride, it should have a 7 hydrogens. Let us see, for example, if it is a propyl chloride, the hydrogens required will be 7 hydrogens, 3 plus 2 plus 2, 7, but only 5 are there. So, you can have an alternatively somewhere a double bond may be there. Okay, right, you can go for that, nothing wrong to guess. So, there is a double bond is there in this compound. So, the double bond means you can have a vinyl or allyl type. Let us have a allyl chloride. Vinyl chlorides react with magnesium less, therefore, let us have a allyl chloride. So, what will be the D means allyl magnesium chloride. Okay, right, it will be the allyl magnesium chloride. And what will be the B? Allyl plus a carboxylic acid. So, this is formed from a ozonolysis reaction. Now, the problem comes, what is that? In the ozonolysis, the compound formed is again is having a double bond. How it is possible? In the ozonolysis, this double bond should be consumed, isn't it? Still the double bond is there in the R, means this reaction is something wrong, or the answer is something wrong. So, therefore, here we have a problem. So, therefore, one should not have a double bond in the R. That means without double bond you must guess the what is this alkyl group, that is C3H5. So, it is not a double bond is correct, but it is the a cyclic system if I propose, then the number of hydrogens will be suitable, 5 hydrogens only. So, here 2 hydrogen, here 2 hydrogens, here only 1. So, therefore, it is the formula C3H5 it is suitable. So, it is cyclopropyl chloride. So, compound C is cyclopropyl chloride. Compound D is not this allyl magnesium chloride, but cyclopropyl magnesium chloride, right? Then it is right. Then what is B means? It is cyclopropyl with the carboxylic acid. This is what your B, which is formed in the ozonolysis of compound A. So, the compound A will have a cyclopropyl carbon, again a carbon with a cyclopropyl this side, that side, but the number of hydrogens are 10 only. That means here 2 plus 2 plus 1, 5 is gone, this side 5 is gone, nothing should be there on the carbons. If I put double bond, you need 2 more hydrogens. So, therefore, there is no chance for the 2 more hydrogen, only 10 is there. So, this must be a triple bond. Okay, finally, we have now come to a correct conclusion. Both the sides cyclopropyls containing acetylene it is. Okay. So, both the sides cyclopropyl containing acetylene is the compound A, which on hydrolysis, oxidative ozonolysis, as per the preparation method we have seen, the alkynes, disubstituted alkynes or disubstituted alkenes, both will give the carboxylic acid. So, this is a 8 carbon 1, 3 plus 4, 3 plus 4. So, 8 carbon 1 cut into 2 pieces. That means you have to take it grand, that it's not given, but you have to take it grand. 2 B's are formed. each one that B can be prepared from taking a corresponding cyclopropyl chloride by converting into the cyclopropyl magnesium chloride, adding carbon dioxide in hydrolysis, the corresponding cyclopropyl carboxylic acid is prepared, which is formed from this oxidative ozonolysis of this compound. The whole story is now we have to remember that if it is a double bond containing compound, the ozonolysis reaction you cannot explain. So therefore, it is not a unsaturated the unit containing, but it is the cyclic ring containing alkyl chloride is the right guess, and cyclopropyl magnesium chloride, cyclopropyl acid, cyclopropyl acetylene is the right way of the answering the question.